Доброе утро, Андрей.
Доброе утро.
I like your background picture. It looks like a nice, what is it, like a tent, or it's a tent?
Yeah.
That's great. Okay, so let's wait for more participants.
Okay.
So, good morning, Natalia. Good morning, Priya. With Andrea, I already greeted. I would say let's just wait for well, I guess another 10 minutes, like yesterday, like a quarter past. I'm not really sure. I heard that only 5 people participated in the practicals yesterday, which is really not much. So let's see. On the other hand, if people come in late, then that's of course also sad. Yeah, good morning. I would say yesterday also some people came in a little bit later, so I would suggest indeed, let's just wait until a quarter past 7. So another 10 minutes, see how many people arrive, and then we start. And if we are just a small group, I don't mind at all. Then we can work together more effectively. That's more in a seminar style. That's fine for me as well. Okay, so let's just wait for another 10 minutes. So good morning again. Well, waiting obviously helped to get some more participants. That is nice. And I don't have my large screen on. I just have to change one more thing here, and then we can start. So, okay, we waited a little bit so that more participants arrive. At 7 o'clock, it was only Andre and me, and then later some more people came. But I would like to start at 7 o'clock, so I will be here again tomorrow. Well, it's 7 a.m. here, so it's very early for me, but it's principally okay. But right now we have a lot of trouble here in our department because we are moving. The whole department is moving to another building, and so the afternoons and evenings and nights are full with packing our stuff to move to another place, which, well, is in a way much nicer, so that's okay, but it takes a lot of time. Good. Yeah, so good morning again, everybody. And again, please speak up if you have a question. And I will, well, it may look funny to you, but you should look at the slides anyways, because I will be using a larger screen, which is for me, for the teaching nicer, but which means my camera of the laptop will kind of, I'm not looking in the camera now, I'm looking at another screen. So don't get here irritated by this, but yeah, also, again, it's much nicer to have a seminar with faces. So spasiba Andre, he has his camera on. Everybody who is comfortable with turning the camera on, I appreciate that. Again, it's nice to see some real people. But that's up to you. Okay, let's do a wrap up of what we have been talking about yesterday. I have to make that other screen here smaller, but it actually, that is irritating a little bit here with the other screen. So I'm going back to my laptop rather. Okay. Now I have. Yeah, what did we talk about yesterday to bring us in the mood to radar remote sensing? I will pick out one or the other of the slides that we talked about yesterday that I think are important. Well, obviously, this concept is important. And so you should see my screen. If you don't see anything, let me know. Okay. That is the concept of the transmissivity of the atmosphere to certain optical wavelengths, and the full transmissibility when the wavelengths get larger than 1 millimeter. And what we have also, or what I have introduced to you, is these different frequencies and wavelength bands, the abbreviations that were originally codes. So this is something you just have to learn. So that is important. Yeah, then there's only a selection of these codes, XCL and P-band, important for us. Because they are available on geoscientific satellites. Okay, we also talked about the electromagnetic wave, the concept of the velocity of light, and so the easy way to transfer or calculate lambda, the wavelength, versus nu, the frequency. So obviously they are dependent through this constant velocity of light. Then I introduced the term amplitude, which is here the power, the intensity of that signal in the direction of the electric field, wavelength, and also I mentioned phase already. So the phase condition is being determined when the wave is being emitted from the sensor, and we also determine the phase condition of the backscattered wave. So this is very unique in radar remote sensing using coherent energy, where you determine the conditions, so peak, so maximum or minimum of that electromagnetic energy, illustrated here as a wave concept. Then we went into the just go to this presentation again. The next important concepts. Yeah, we talked about several aspects that we could see on these multi-polarization false color composites. Yeah, zooming in, so we talked about the concept of radar shadow, of the illumination direction. Then, yeah, because we'll talk about this again. Yeah, here we have a multi-polarization color composite on C-band, L-band, and P-band, which is the wavelength of the new ESA satellite biomass to be launched in a few years. And that we do see with the longer wavelength, 70, 80 centimeter wavelength, almost 1 meter. Of course, we see very different aspects of this land surface. We penetrate tropical forests. Okay, what else to repeat? Yeah, now we will continue here today again on SAR concepts. So this is important. Radar sensors look to the side. Then we have an illumination footprint that is determined in range. So that is one of the terms introduced to you. In range, it is determined by the width of the antenna beam. And in azimuth, obviously there's one of these antenna looks one after the other is being assembled to form eventually an image, a radar image illustrated here with in that rectangle. Okay, I think that was also an important concept, that looking at least we talked about this concept of synthetic aperture radar. Meaning that the aperture is the antenna, or that determines the antenna beam opening. So a real aperture could be something like 10 meters in space, 10 or 12 meters. And with that size of the real antenna, we would have a very wide antenna beam. So here in near range, well, the waves, this would be the extension of the wave front being emitted from the sensor, hitting here this object D1, but the resolution actually is determined by the width of this antenna beam. But here in far range, we would have a very wide antenna beam and we would not be able to detect an individual object. But using the concept of synthetic aperture radar, which applies the Doppler theory, we synthesize a much larger antenna, which is indicated here by A2, because at this position, we reach or we receive backscatter from this position D2 already here in our wide antenna area. And while the antenna moves along, this object is being observed in this antenna beam, and then here in the next one, and then here it has the shortest distance. And so here it will return backscatter signals in the frequency that has been emitted. But here the frequency of these backscattered signals will increase and then decrease. And I introduced this analogy of a little ship crossing. You throw a stone in the water, and then you have these wave fronts going away from where the stone fell in the water, and the ship is crossing while it's moving towards this emission source. It has to move over many more little waves than when it is moving away from the emission source. So this is exactly the same what is happening here. That or the other analogy is the train emitting sound while the train moves towards you, the sound gets higher and higher, and when it moves away, the sound gets lower. So you can actually determine where the train is by measuring the frequency of the tone. So that's the same idea here. See, I read another term here, swath width. Of course, this determines the image covered, the swath width, and it's always a bit to the side of the nadir track of the satellite. And the reason is that we have to distinguish where a pixel is located by the range, by the time the signal needs from the radar to the ground and back. And so in nadir, this would be in a radar altimeter, for example. It's only a point source measuring, again, via the time, for example, the ocean height. But it's not an imaging radar. Imaging radars all have to look to the side. Okay, then another term was the pulse repetition frequency, between 1,000 and 4,000 hertz. I mean, how many of these signals are being emitted in 1 second? We come back to this today. Well, and this is all very fast compared to the velocity of the satellite, which is only 7 kilometers a second, or as any of our satellites or the space station, 90 minutes per orbit. So 1.5 hours is one orbit. Presentation, just repeating again. Yeah, and then very important here, this concept, which looks like a lot of trouble, depending on, well, obviously how steep your terrain is, but depending also whether you are looking in near range, mid-range, or far range, you have 3 different geometric distortion effects. Now, one is the layover here very close to the sensor, and it's all very logical because the location on your image, on your slant range image, is determined by the time again. And so if this signal comes back first, it will be located first on your image, which means there is a layover because only afterwards all the returns from the slope occur. And then we have this extreme phenomena where the whole slope is in the geometry of one wavefront, and this is called foreshortening. And it may mean that the slope is being shortened up to the extreme of only being one line. Well, and the last one in far range is then shadow. So this all sounds like a big problem, but as I showed you on this image, if you, because you can draw it, maybe you can say it in that way easily, yeah, because you can draw it, you can model it. So what is being done is that an elevation model is being used, and you simulate the respective radar geometry, and then you would overlay that image and then transfer it back to an elevation model geometry. Yeah, so, but still we are losing areas. We are losing areas where we have that layover or where we have foreshortening. So we have to look on topography from the other side. We always have to look from the different sides around a mountain to form a full radar image of all sides. So that makes it difficult, but all of these, let's say the programs, the software is available. And since the satellites, especially over Russian territory in the northern areas, you have a lot of overlap of your orbits. So you don't only have the crossings of ascending and descending, you also have overlapping swaths because they all meet over the pole, obviously, because of the shape of the Earth. So you reach a very good coverage from several looking directions. Okay, and I think with this we reach a part that, yes, oh no, we have talked about some of this. Yeah, this is another important concept here, the concept of the decibels, which is first very unusual, but it is being used since we are always receiving if one would be the full power, so everything that has all the energy that has been emitted is coming back, then we would have an intensity value of 1. But usually we receive a ratio only of what has been emitted, especially from natural targets, fields and forests. We only receive a very, very small signal. And to make that signal visible in an image, we need to apply the logarithm, and then we would have negative numbers. That is, well, a bit inconvenient, and also it would be small numbers, 0.1 or 0.2. So as a convention, we multiply it by 10, and this is how we get to these strange numbers. And this is, I think, about where we ended up yesterday. So these are the range values. If we have a smooth surface, calm water, or the oil surface that we saw yesterday, we get below minus 20 dB, we reach minus 30 dB. And usually we have values between minus 10 to minus 20. Now, a question you could raise is, well, how exact is actually a radar measurement? And the answer here is, for modeling approaches, for example, for a soil moisture retrieval, we expect that the sensor's sensitivity is about 1 dB or perhaps better. So with the sentinels, I think they say the margin is the measuring accuracy can be up to ½ dB. So I'm saying this that you shouldn't worry whether it is for many of the applications, whether you measure minus 10 or minus 11 or minus 12, minus 13. So 1 dB is that sensitivity of the sensor. Anything beyond that ½ dB is in the noise of the measurement system. So we can be exact up to 1 dB, but with a let's say plus minus 1 dB margin also. Just when we start interpreting radar backscatter values, don't fix yourself on 1 dB, rather look at a range of plus minus 1 dB. Okay, but altogether we have not so the range altogether is not that large. Usually, let's say from -5 to maybe -25 dB. So that is the variation that we have from natural surfaces. Okay, that is something that's inconvenient. I have negative numbers. Oh, and there's one more for if you do calculations, you have to be aware, but again, this is all part also of the respective softwares, because the dB is a logarithmic number. Whether your multiplication changes into subtraction and differences into ratios. So you have to be a bit careful what kind of mathematics you apply using the decibel numbers. So of course, we use decibels for visualizing the radar results, but it is also absolutely appropriate to apply your model to the decimal values. Then you are working, let's say, on the direct measurements numbers, and you are in a decimal world, which is absolutely fine, but you will see that your numbers are very, very small, because you are here in a range of 1 to 100, or if you go even below -20 dB, then you reach to 1,000th part of the energy being emitted. So it's very small numbers. But anyway, so both is of course possible because both is correct. Okay, so then we move again here to the. So any questions from to that material presented yesterday? Okay, and I see one more face, Yakimov. Thank you very much. looking at a real person is indeed much nicer. So maybe we can get some more faces here. We have some more people joining in, and I think it's also for you guys nice to see each other. But you'll do as you feel comfortable. Okay, now we move on. I go in the presentation mode. I finished yesterday. By pointing, and this list is not really matching to, like I would reduce these effects between sensor parameters and surface parameters. So I usually like to say we have 3 types of sensor parameters that if we start interpreting a radar image or we want to plan a radar mission, then I have to consider, okay, what are the 3 sensor parameters, which is wavelength, polarization, and look angle. And I mean, obviously the geometric resolution comes in there too, but that's, well, let's say kind of like a natural fact that you have in optical images as well. So wavelength, polarization, and the incidence angle is important and governs what I can detect. So I always have to first ask this question: wavelength, polarization, look angle. Okay, on the surface, again, I can say it's 3 things on the surface. It's the surface roughness. It's the geometry. And when I say geometry, it actually includes here the geomorphology, because the geomorphology I would see only if there is no vegetation. But if there is vegetation, then it's the geometry of the vegetation that I'm interested in. And the last one is the dielectric constant. So, but here it's more an extensive list. I think it's for, if you start with radar, then it's easier to remember these 3 things on each side. Wavelength, polarization, local angle, and on the surface side, it's the roughness, it's the geometry of the scatterers, and the dielectric constant. And the dielectric constant, it sounds complicated. What it stands for is the moisture. It's either the soil moisture or the moisture in the vegetation. So here it's a bit more extensive, which is of course also correct. Yeah, the local slope, the orientation of the slope is important, as we have just seen. The geometry takes effect. Yeah, and then what we observe is, and it's written in here, what we observe is the surface scattering, or it's a volume scattering, and here the double bounce is a specific type, actually, of a specular reflection on the surface. So far, we have talked about the specular reflection and the diffuse backscattering and volume scattering and double bounce. We will talk a bit more about now on canopy, but it's also interesting at trunks or buildings. Okay, yeah, a corner reflector is often being used for radar calibration because these tetraeders, you see they're constructed by the German Space Agency. This is in Egypt. And this is actually in front of Lake Baikal, what's it called, the Sverto Morde, it is near the Selenga Delta to Baikal. And this is many years ago, 20 years ago, in a cooperation we had with an institution in Ulan-Ude. And these tetraeders are built to calibrate your radar system or the image that you receive, because you get a calibrated backscatter from such metal objects. And it is also used to co-register your image very well to a high accuracy. So if you know the coordinates very well of these tetraeders, and then they are being oriented, as you can see here, towards the sky. So this was done during a space shuttle mission in the year 2000. You get a very strong signal. Maybe you remember from yesterday, we had these star-like signals on the images. You get a very strong signal from this corner reflector, and then you can identify the pixel exactly to this ground. And you also, because it's a very strong signal, you can calibrate your radar image. So this is a technique that is, or rather, let's say, has been used. Meanwhile, and also this was especially important for a space shuttle mission, the Shuttle Radar Topography mission that produced the SRTM data set. Maybe some of you have worked with this free digital elevation model. Nowadays, the calibration is usually done with active calibrators in the countries that run the satellites. So a European satellite would have a calibration system in Europe, and that's enough. It's indeed enough to have it at some few places, and just to observe how the radar sensor, how it is working. But what I wanted to show here with that corner reflector is what is happening here is exactly that double bounce I wanted to introduce to you. So you in such a corner reflector, in this tetraeder, you always have two bounces. So the radar would either hit the ground or the side, and then it would be forwarded specularly, so a specular reflection, and then hits the next side, and then is being transmitted back to the sensor. So this is why the power is almost fully retained of that signal that is hitting the corner reflector. So that's why we use it in calibration, but the same is happening here, just to go back, when we have, especially, of course, buildings, that what we saw that yesterday, you have the same, you have a rectangular angle of a wall and the surface, and you have the same phenomena happening, in so-called double bounce. First on the ground and then on the house side, or the other way around. And also what is an interesting double bounce feature is when you have wetland areas where you have forests. So you have larger trunks or tree trunks standing in water. Then the same thing is happening. You have the water surface and you have the tree, and you have again a double bounce because water, you cannot penetrate water, so you have a specular reflection. And on the tree trunk, which is full of water, obviously, you get the next specular reflection. So it's a very nice, easy method to map where you have flooded areas flooding into forest areas. This is obviously in the Amazon area important, because the Amazon River has a water level change of 12 meters. Yeah, depending on the precipitation in the Andes, you can have flood events of up to 12 meters. So it's a huge area that is being flooded and is contributing methane to the atmosphere. And there's no other way to map it. So an overview here of the satellites, again, I've been mentioning them before. Yeah, the shortest wavelength X, TerraSAR X is a German system, TerraSAR Tandem X, producing an elevation model. Now here you have the list of the Seabend satellites, starting with ERS 1 and 2, and now please try to remember the names, because they appear now in the examples again and again. RadarSat is the Canadian Seabend satellite, and then we have Envisat, which was launched in the year 2000, following ERS 1 and 2, also Seabend, and now we have the Sentinels. So in Seabend, we have a history starting with ERS and RadarSat. There's also several RadarSats now run by the Canadian Space Agency. So we have now 30 years of Seabend data time series, which is quite something. Then ALOS and JRS-1, these are the Japanese satellites. They have been focusing on L-band, very interesting frequency. But unfortunately, the Japanese turned the data policy into a commercial system. So the L-band data are quite expensive. But starting next year, we have an American-Indian cooperation, NISAR. So NASA and ISRO are launching a L-band satellite together that will be very, very great for all kinds of research, especially related to forests, forest densities, forest biomass, etc. L-band is the best wavelength, and the data will be free. Okay, this is just a summary again of the advantages of a radar system. And again, I'm using SAR or radar almost simultaneously, because all the radar system we are using now use or apply the synthetic aperture technique. It's active, so it's independent of sun illumination, which means you can detect, or no, you can receive images on the descending orbit on the sunny side of the Earth. Now for the 45 minutes, the satellite flies south, and then it flies 45 minutes up again on the night side. And we can use those images as well. And this already gives us two look angles. Yeah, we have an ascending and descending crossing. Okay, it penetrates clouds, partially penetrates canopy soil snow. It's coherent. So we know the phase it's being emitted, and this allows us to apply interferometry, but it gives us also the problem of speckle we will look into now. Polarization can be exploited. So all, as you see, we have on satellites only one frequency or one wavelength. We do not have multispectral systems like in optics, just because it takes too much energy, which means we have one wavelength only, but we can exploit polarization, HH, VV, the co-polarized or the cross-polarized, HVVH, also introduced yesterday. And obviously spatial resolution varies a lot, especially in the spaceborne. We will look at that. The technique in a minute. Good, I think this is all clear. What this comparison shows, again, as an example, when we compare X-band or C-band and L-band, we saw that yesterday already. Now, what becomes important, where is what we say the scattering, where is the scattering center, or where does the scattering originate? And if we have a short wavelength like X-band, yeah, the small 3 centimeters, it interacts with everything that has that size. So at this image, this is here in Thuringia, just a bit south of our town Jena, where my university is located. This is a very nice mixed land cover. And when we start here at the upper image, we see, I think you can also already from the features, yeah, imagine that this may be forest here, this bright stuff, then here the little pointy things, but bright returns, that these are villages. You already learned there is specular reflection from, or can be specular reflection from water surfaces. If they are smooth, yeah, obviously here this is a little dam, water area, black, because obviously no wind, no currents, very smooth water surface. And then we have this in-between thing here, which is fields. And in L-band, we see a big difference. And now you could already apply your knowledge on the scattering mechanisms, and you say, okay, this is specular reflection. Here we have obviously a lot of returns. It's very bright. So yeah, it must come, it can only come from a volume scattering, perhaps this double bounce, which I just mentioned. No, but for double bounce, it means that the surface below the forest would have to be smooth or very wet. So, well, just knowing the geographic area, we don't have flooded forests here in Germany. So this is really returns coming from the trees, the trunks, and the stems. So volume scattering from the forests. But here in the fields, the L-band with this long wavelength over 20 centimeters, there's a lot of specular reflection happening. Yeah, it's being scattered away from the antenna. Here it's a bit brighter, so there is some backscattering coming back. But the difference between that scattering mechanism in the forest and in the agricultural areas is very, very large. Yeah, there's quite a dynamic range of the backscatter values. And if you look at the X-band, and if you would have a C-band image here too, it would show this a similar thing. We are moving here, the interaction is with things on the surface that are, let's say, 23, 25 centimeter long. Now, so that is why we see the forest bright, and of course in the villages, it is corner reflection that governs the backscatter mechanism. But here in X-band interacts with little things, so even grassland or small plants on the agricultural fields, they already also cause volume scattering. So the scatter mechanism on the fields is very similar to the forest. And that is why you do not see such a big difference between a field and a forest. Now we see bit shades of gray, but in general, the amplitude or the intensity of that backscattered signal is very similar. So looking at these smaller wavelengths, if you have only a single image, it can be quite difficult to discriminate grassland, agricultural crops, or forest if you have only a single image in X-band, and the same is true for C-band, just because the wavelength is so short. Now, and these two images demonstrate that very, very nicely, that the length of the wave is obviously important, is very important. Yeah, so with an image like this, you couldn't do much. So what you need is then either polarization, or of course what we have now is the wonderful time series of Sentinel-1. Yeah, but just remember these two images as the big impact that the wavelength has. Okay, we have introduced that. We have already talked about polarization. This is an old image from an American textbook that is being used again and again, just to illustrate really how simple or how physical, how geometric we can imagine what the radar wave and the interaction with the surface is. So they have this magic hand here that's swinging the wave in vertical plane to the Earth's surface. So VV means what I said yesterday. You send out vertical. On the surface is all kinds of scattering happening, but you are still only observing the vertical backscattered waves. And horizontally indeed means horizontal to the Earth's surface, and HH, the co-polarization, HH means also the backscattered horizontally polarized images, or only those are being received. And a full polarimetric system would be able to simultaneously, which still means, well, like one pulse is vertical, the next pulse is horizontal, and then also with the receiver, it receives one time, it can only switch between vertical and horizontal, and it switches again to horizontal receiving or vertical. And remember, we have systems that send out 1,000 up to 4,000 pulses per second, and this is how fast the system changes back and forth between sending and receiving. But this is technical stuff, and I think most of you are actually more geoscientists and not radar engineers. Yeah, and this is, we're looking at the same area that we just saw, but now a color composite, similar of what we have seen before, showing you the difference here or the impact of the polarization. And here we have a similar phenomena like yesterday. We have an electricity line here going through the image parallel to the flight line. So the HH polarization, you can still see this here, HH is in the red channel, VV in green, and the cross-polarized is in the blue channel. So the red is picking up this phenomena because it's parallel. So red and green forms yellow, and what you can see here is that these co-polarized signals very nicely pick up here the rows in these fields. Probably freshly prepared by a bulldozer, and in these where the big tires moved over the ground, you do not have any vegetation standing, so you do not have any cross-polarized backscatter. So everywhere where the blue comes in, which is obviously the case here in the forest, there is volume scattering. Here is a field, a white field, which means we have backscatter from everything. We have HH, VV, and HV, forming a white return. Means obviously this is an agricultural crop, something with a lot of volume, maybe a cornfield or a rapeseed field, but something that is causing also a lot of volume scattering, because the cross-polarized signal stands for volume scattering. So here we can see with the polarization, we can start interpreting or classifying such an image. Okay, we move on to time. SAR missions, and we can go quickly through those. I have mentioned them before, and again, I mean, if you're a newcomer to radar, then it's always difficult to remember all those names. But they're not. Let's see, with the optical sensor as well, there's also an optical, we have Landsat and then a few others, but the working horse is, of course, Landsat, until now Sentinel-2 since 6 years. But in radar, it's a bit more diverse, and I think that's why it's good for you to know that there are these different nations applying different wavelengths. Because to get something like a multispectral image, we have to put images from several satellites together. That's unfortunately the fate in radar remote sensing. Now, so here the C-band, L-band sensor, and they all have the same geometries. Now the large microstrip antennas that form the radar signal, radar SAT. Actually, Sentinel looks very similar. And then you have the solar panels giving energy to the system, because radar needs a lot of power. So here, for example, EOS is here, very large solar panel. And this is actually not such a nice presentation of Envisat, because Envisat had 10 different sensors on board. And the solar panel here, it's still folded. It's the largest solar panel satellite ever had, because it needed so much energy. Very flexible solar panel. Yeah, TerraSAR X is a bit is very simply built. And so yeah, there's one aspect, and they have been using it for Sentinel-1 as well. If you use optical data, you know that the acquisition time, the local acquisition time, is always in the morning, 10 or 11 o'clock. And that was specifically designed that way to avoid cloud building during noon. Yeah, when you have in the morning, it's still moist, so you want to be out of morning dew or night effects. But you also want to avoid with optical data that you run into the noon time. So we are used to having local acquisition times of around 11 a.m., let's say. With radar satellites, it started the same way, to have a similar ERS-1 and 2. They had acquisition times also in the morning. But it turned out, and TerraSAR X was, to my knowledge, the first implementing that, that for a radar satellite needing continuously solar to charge its solar panels, they started here with TerraSAR X to fly the satellite exactly on the day-night border, let's say. So this satellite takes images in the morning at 6 a.m. and in the afternoon 6 p.m. so 1800. And this is why it doesn't have that kind of flexible rotating solar panels anymore. It has one fixed solar panel always facing towards the sun, and then here to the low to the earth, of course, is the large radar microstrip antenna taking the backscatter from the earth and sending out the signals. And well, this thing is just a communication antenna sending the data to the ground. So it looks much more simple. It's a easy concept and nice to launch, because you do not have to unfold anything. It's just like a little cylinder that is being launched. Okay, here's Sentinel-1. You see it looks similar to the radar SAT. Here is the large microstrip antenna, which has 10 or 12 meters. I don't know exactly, but when I mentioned the 10 meters, you will see them later. So this is what we would call the real aperture, the real antenna length. I think it's 10 meters, possibly 12, but in that range. Yeah. Okay, here is an overview of the different wavelengths being used and the satellites up in space. And as you possibly know, there is more and more coming up. There is a lot of commercial activity. Yeah, ICEYE, a Finnish satellite, Earthcast, and what is it, British Canadian, I think. So you can actually watch the commercial business developing around radar satellites. It's like the new hype in commercial remote sensing, because of its advantages. You can acquire day and night. You have if you have a high geometric resolution, and the commercial satellites have high resolution, 1 meter or better, you can detect especially man-made objects very well. So the commercial are more looking on infrastructure and there are more infrastructural development than land surfaces. But again, it's filling up space also with radar capabilities. Now here we have the three wavelengths. Again, the European and Canadian developments. Here's 1, 2, Envisage Sentinel-1. And also, if you're not familiar, a Sentinel is a fleet of satellites as part of the European Copernicus program. And this program started in 2015, and now the satellites, they're all, so Sentinel-1 is a radar satellite, and there is like, all of them are called Sentinel-1, but A, B, C, and I think C is being, A and B are up, C is soon being launched, and the money, well, I hope it stays that way, will also continue for the next decades. So with the Sentinels, you really have a monitoring system. It's free data, wonderful geometric resolutions, and it will be, so if you develop a model based on Seabend Sentinel data, you can apply that model for the next 2-3 decades, assured. So yeah, Sentinel-1, A and B, Sentinel-2 is the optical satellite, same thing, A, B, C, so every few years a new satellite is being launched. And here we have the Japanese L-band. Now, oh yeah, the Brazilian Sarcom, they launched another L-band satellite, and NISA is up next year. So there is a lot in space, and I can only encourage you to use different satellite data, yeah, to get a better picture. It makes more fun, of course, with different frequencies. Yeah, there was a satellite CSAT in the 70s, and it was built to observe the ocean surfaces. So the history goes back here to 76. And then there were the shuttle campaigns, shuttle imaging radar A, B, and C, and this is where the Germans participated with the X-band Sar. So this is the only 2 shuttle campaigns where we had, and this is why it's colored, we had XC and L-band in space. And based on this success, SRTM was launched in 2000 February. And shuttle missions can only take maximum 11 days. So they collected data over 11 days, and SRTM indeed managed to produce a global elevation model within these 11 days. So an exciting work. What is actually, I'm just looking here, what is missing here is the Russian satellite. There was in the 80s, there was, and the satellite was called Almaz, and it was an S-band satellite. So S-band is here, I mentioned it yesterday, it's 10 centimeter wavelength. So it would close that gap between 3 and 5, and here over 20 centimeters. So it's really a wavelength necessary, and I think the British have launched an S-band satellite now. Also, it's partially commercial, but it's something to watch. Yeah, what's the development here? Okay, so I think we're running a bit, but we started later. But I'd like to give you all a break. Let me just see whether we finish this part, how many. Oh no, this is a nice examples. We should talk a little bit longer. So I would suggest let's have just a 9-minute coffee break and meet again a quarter past. So, or any questions? I should give you the possibility to ask questions too, of course. Anything to that material? No? Okay, then, well, I think it's nice to see you and see faces. Andrei Yakimov, thank you very much for giving me here an audience. Okay, see you in 10 minutes. So, okay, let's continue. With further applications. Okay, so this is just a list. Now, we have talked about all of this except interferometry, where we are getting. Wait, did I turn on? Yeah, all of this list I talked about. Structure, we have to focus a bit more on, yeah, subsurface penetration. I have also some slides in the next lecture. So this should be, I think this is all clear to everybody. Some examples here from Terra X, Brazil, showing you again, when you see a black surface like this, can only be specular reflection, so very smooth surface. We see there is some impact of illumination and also a bit of, not an extreme radar shadow, but due to the illumination, we can see nicely here these gallery forests along the rivers. Here we see some meanders. So we see different vegetation types here. And so again, yeah, remember now we're looking at the Terra X image, X-band 3 centimeters. It will not penetrate much into the canopy. Actually, it was found that in general, if you have a closed forest canopy, an X-band may penetrate to about 1 meter, 1 meter. That's so it means the returns of the X-band signals comes from the upper 1 meter of a vegetation canopy. Now, if it's a very sparse canopy, it can go a bit further, but that's about where the backscatter comes from. So this is all what we see here as information is a return related to the structure of the vegetation. Yeah, then there are things like the pulsar 10-meter global mosaic, which is nice if, obviously, I mean, there are projects that I would like to mention here, global projects. The European Space Agency has a series of projects. If you are interested in applications, look into, they're called CCI, for Climate Change Initiative, CCI. And there is maybe 15 very large programs with the best remote sensing experts they could gather, looking at, there is, for example, a CCI soil moisture, looking especially on how to monitor soil moisture on a global level. Or there is a CCI biomass, where we are also a member of. And these CCI projects, again, CCI stands for Climate Change Initiative. Now, they have the task to contribute on a global level to what has been defined by the IPCC, the International Panel for Climate Change, has been defined as essential climate variables, and there are several. So for such large programs, we need, of course, global products, and that is why JAXA, the Japanese Space Agency, produced here and is continuously producing such global mosaics that they are then free to be used for everybody, and can be a good contribution if you work. Let's say you do not necessarily have to work globally. I mean, you see the large territory of Russia. But even if you focus in a region, 10 meters is already a nice resolution and comparable to Sentinel. So there are products available, and you see here pulsar system. Pulsar is the sensor, and ALOS is the satellite. That's why you saw ALOS before. Here you see pulsar. It's like one ALOS again is the bus, the satellite bus, and pulsar is the radar sensor. It works in HH, and so you get the co-polarized and the cross-polarized HV. Now, again, this is L-band, and you see already on the global map what you have seen before from an airborne scene in Thuringia. The difference between forest and non-forest is very nicely observable. You do not have to do much anymore to produce a forest map. But of course, L-band also gives the possibility to retrieve biomass. Okay. Yeah, that's what we looked at before, just comparing L-band and X-band as a gray value image. And here we have a color composite now, the same area. And now putting X-band and L-band together, now we start to see that the color comes into our image. And that, of course, as in a multispectral color composite, means information that can be used for classification or monitoring. Okay, this has been discussed before. Yeah, well, the word classification, of course, that is something, so cover monitoring is possible. Yeah, this is an example from our projects in Siberia. We were working together with the Russian Forest Inventory and, of course, with the Sukachov Forest Institute for, let's say, almost 20 years on applying methods on mapping the Siberian forest territories. And so that all started in the late 90s and went on until about 2010. And this is just a comparison of a Landsat image here from 1990 and an image here from 2006 using the Envisat ASAR data. So well, you see some of the areas of the logging areas have extended and some are being regrown. But why this image is important is obviously that you can observe the forest areas also in the winter time, where you have, depending on the cloud cover, trouble to receive respective optical data. Yeah? If you have a nice image like this, and this is why forest inventory is, of course, based on optical data, then this is much easier to interpret. But now with a time series, you have also a tool, also with a 10-meter resolution, that is a good monitoring tool. What you see here, in a way, shows again, if you have only a single image, you have this speckle, this noise. It looks like a noisy image, which makes it not so easy or convenient to interpret. And again, ASAR is the radar system that was on Envisat. It's only Seabend. Seabend is the 5-centimeter wavelength. So it does not discriminate so well between forest and non-forest. So you need time series to have a better monitoring tool. That's, I think, the only solution if you have a Seabend signal, or to apply interferometry, but we will come to that. And here again, ASAR, HH, and HV. And yeah, if you want to produce a color composite, you can use ratios. And here in the blue channel, HV divided by HH is adding a third. Yeah, and this was the same here at the pulsar. HH divided by HV, just to have a third channel in your color composite, because the input is only 2, HH and HV. Good. Yeah, and this is, of course, I mean, such, here we have the Bratsk dam area. This is the Angara river, and just zooming in here in a territory over the different years. Obviously, you are able to map in a good way the change in forest cover that is happening. So no surprises. Another application example is using radar if you have a rapid need, because again, you are independent of cloud cover. This is another example of an oil spill, what we've seen yesterday here in the Gulf of Mexico, again showing the difference of where the extension of the oil spill, because it smooths the surface and you get specular reflection. And well, yeah, this is a comparison to an optical image. A few days later, only there was a cloud-free image before there was cloud, or in this case here, that was an oil platform was burning, and you have a big plume of dust above the area, so you cannot look through the plume. And also with radar, this is no problem. It's a very also for volcano eruptions. It's very dry dust plumes and clouds. So for the radar penetrates and can monitor. Retrieval from radar. This is also one of our cooperation projects with Russian colleagues on applying this NVSAT-ESA system now on a global way. This was the first time that radar was applied in a model to retrieve globally biomass. So what you see here on the right side, the legend, is the growing stem volume, which is the parameter coming from the forest inventory, cubic meters per hectare. And here, over a whole year, data has been acquired and then implemented in nothing very special, in a regression algorithm, just a regression with a growing stock volume from the inventories. And it turned out, and that was at that time a surprise for us, that looking at multi-temporal data over a whole year, the regression allowed a retrieval up to 350 cubic meters per hectare. And that's about a good maximum, especially in the Russian territory. Not, of course, in the tropics. So here you see we even had to cut out some areas just because the C-band from the NVSAT-ESA is not long enough to give any good correlation to tropical biomass. Just too short, the wavelength. Locally, it can turn out actually very nicely. Here is a comparison. So for our regional applications, this is our state of Thuringia. So this is a growing stock volume map of Thuringia. And here we go up to higher cubic meters. But this has been also applying now L-band data from the Japanese satellites. Only then you are able again to develop a regression to higher biomass amounts. And here on the right side, you see a result of a PhD from a Polish student that worked with us, Martina Stelmaszuk-Boska. And she had been closely cooperating again with our Russian colleagues from Sukhachov Forest Institute to produce such a growing stock volume map of the Siberian test sites. So this is all regression based. We will, I think tomorrow, also look into some of these models. But it needs multi-temporal data. Not a single date would be sufficient to develop such a regression model. Okay, so where we are now is obviously moving into what we call hypertemporal radar time series. So during the German word here, Zeitreihen, a time series. And hypertemporal means that we are extending over, like it would be for hyperspectral, you say more than 15-20 channels is hyperspectral, so we would also say more than 15-20 acquisitions per year. We move into a hypertemporal time series. And if you look at this is on the left side, again, from the NVSAT ESA data, and this is the optical data. Now the colors, even though they're still kind of similar, but you start to look into variations that are comparable to optical data. And again, for agricultural monitoring in Germany and many parts of Europe, we have big cloud problems during the growing season. We have very often cloud cover. So we just do not have any optical data available. So now we are changing to filling up these gaps with optical data. Yeah, and this is just one example, and I will show you more of this. It's one approach to the hypertemporal time series. This is an image transform based on what's called a temporal decomposition. When you look at the original data, this would be the time series of the original data. But radar data, because of this speckle phenomena, it's not this nice time series like maybe you are used to it from NDVI. You see variations, but you have a lot of dynamic spread per temporal date. So, and this is from an area in tropics. And the question is, how do you move on? You can try to apply all kinds of smoothing algorithm, but if you smooth, then filtering, a temporal filter, but then you're also reducing the information that you have available. So this temporal decomposition method, what it applies to is kind of a frequency analysis, looking at kind of similar to a Fourier analysis, looking at high frequencies of different frequency elements. Now that you separate here, so this would be the noise, and only in the second and third modulation, you start to see, like this, for example, looks like a nice representation of the dynamics in this area. And in looking or demodulating it further, you may be able to detect even in a change that looks here kind of arbitrary, you may detect trends. I'm not sure what we did with the residuals here, but to complete the image. So another approach is, of course, so some of you are also applying machine learning. Obviously, we are doing that too. With the machine learning approaches, the problem is that you need, the same as for artificial intelligence, you need training data. So your result is as good as the training data that you have. And that's an old problem in image processing, the old problem of supervised classification versus unsupervised. I'm a big fan of more letting the data speak, apply data exploration, apply hybrid approaches. So what we are doing now is first apply K-clustering, so a traditional unsupervised clustering algorithm to segment. And what we are working on right now is to develop spatial temporal segmenting, which means one aspect is, of course, the temporal signal, and where we have to smartly develop temporal signals, or let me call them temporal segments, to detect what is this temporal phenomena that makes this site specific or distinguishes this pixel from another pixel. But then there's obviously also spatial information. So with segmentation algorithms. I mean, there are plenty around. Ecognition is a very famous software, but there's many softwares offer segmentation algorithms that could also be an approach to work spatially. So, but obviously now having time series of, depending where you are, we work a lot in South Africa. There we have only descending orbits. We have only every 12 days a Sentinel-1 image, which still adds up to 140, 150 scenes per year. Here in Thuringia, we have descending, ascending, we have overlapping swaths. So we end up with 400 to 500 Sentinel-1 acquisitions at a certain location. And this is, of course, very exciting, very challenging. And I think, so this is where a few groups work on these mostly machine learning approaches, but we would like to bring in more data exploration and the physical meaning to the data. But we will talk more about this. Okay, this is just a list of all kinds of applications. I don't have to read that. I think you all know, or you can then read yourself. And we finish this with a little excursion on the speckle. Okay, again, another ugly image. And the speckle originates from actually this phase noise in a resolution cell. So there's nothing you can do, or there's nothing we can do about speckle. It's inherent to the system, to this technology. So we have to live with it, and all we can try to do is, just going back to the image, is try to apply smart filtering. So in image processing systems, there's several radar filters, and for your specific application, you should just try them out. There's not one recommendation, because a filter, if you have like a mean or median filter, it would smooth out also the borders, which you don't want. So for radar, you need smart filters that try to decrease that speckle effect, but still keep the borders. And there's a like frost filter, map filter. There's a long list available to do that. Another approach is to look into the temporal signature. So not to look in the pixel surroundings, because the speckle comes and goes, but to look at one pixel through time and then smooth the temporal signal. So that is, of course, also with increasing temporal acquisitions a possibility. This is just about the phase of the signal, but this is the important graph showing the problem. If this is one pixel, okay, and this is supposed to be an area that, there is, well, think of the Sentinel-1 resolution, 10 by 10 meters. In a 10 by 10 meters, even if you think it's a homogeneous surface, there is still variation. There may be little stones, there may be different types of plants, even in agricultural field, there may be some weeds covering the soil. So there's always some heterogeneity in that 10 by 10 meters. So the incoming wave, our radar wave, is hitting the 10 by 10 meters, and it undergoes various backscattering procedures of this, or in this resolution cell. So this is what is here being drawn, that you have multiple scattering, and each scattering causes an amplitude. So the power of that returning signal, and it causes a phase shift. Now we have coherent radiation, and each interaction causes a phase shift. So to explain speckle, these little graphs are often used to show how these individual interactions within a resolution cell, so this is here 1 pixel, now can add up, and that's more an arbitrary process. They can up either constructively, so this is indicated by this long red arrow. This would be a large signal, and the direction of that arrow has to do with the phase. So, but here we're looking now just at the gray values, and this is a very bright pixel. Or it can happen that this is just destructive addition of scattering mechanisms, like in this pixel, it's the same surface, but just because of the summing up arbitrarily these different backscattering mechanisms, it could be that it is a destructive effect. So indicated here by another phase and a much shorter red arrow. So this would be a dark pixel. So the good thing is that it is still, in this example, it is still the same surface. So if this would be an agricultural field and you would look at more and more and more pixels, now you have constructive and destructive speckle, but in the mean, averaging over the whole field, still the reply, the backscattering reply is relatively similar. So even if you look at this very, very ugly image, is of course an example for very bad speckle, and this is how maybe 20 years ago radar images from ERS-1, this is how they look like. Now still you see, okay, here in that area it is darker, but we have that variation, or here it is more grayish, and we have that variation, or here in this probably forest area, it is brighter. We still cognitively recognize these are different surfaces. So in a mean, the speckle is sometimes hidden in a principally higher backscatter, or it's hidden in a principally lower backscatter. So that's a good message. But so this little excursion towards speckle is just to give you the information. There's nothing you can do about speckle. It's part of the radar image. Okay. Yeah, and well, if you have a nice speckle filter, but this is from an airborne image, yeah, you can here some Bayesian algorithm. You can actually retrieve. But this looks very nice. It looks maybe they did some also multi-temporal processing. But this is of course a very nice example how you can change an ugly speckly image into something nicer. But I think that example here also looks so nice because it's from airborne and you have the high resolution. But so there's something you can do about it to a certain degree. So, okay, yeah, this ends this first introduction, and I would like to move on right away to the second lecture. Any questions so far on speckle or the concepts? Okay. Good. I see also no chat. Then we stop this and go to the next. Okay, so here, I mean, the material we are using comes from the EU College, as you know. And so I have the pleasure to present here material from Professor Eineder. He is one of the leading engineers at the German Aerospace Establishment, and he is also teaching at the Technical University in Munich. And he's really one of the, well, also decades of experience in radar, but I think he's also a very good teacher from an engineering standpoint. So he is an engineer. So you will see that at the following slides, and I can use them in the frame again of our EO College, which is our platform for digital teaching. And please explore the site. There are different massive open online courses and MOOCs that you can follow up. There's thousands, literally thousands of slides where you can then also go in more depth than what we can do here in a short week course. So please check out the EO College website. Okay, so we look once more into radar imaging, deepen the knowledge on the processing and the characteristics, and go into examples. And I hope we can finish, but I think we should be able to finish this. So some of that is repetition, because this is now from his view, from his lecture, so we can move faster over it. Well, why SAR? Yeah, he uses this example, of course, because well, some part of the Earth is in night, and also we have a lot of cloud coverage. So that's a nice example why we should, or why we have to use SAR to be able to monitor. We have different resolutions, and yeah, here you can already observe your knowledge or apply your knowledge. The smooth, this is the DLR location west of Munich, a very beautiful Bavarian landscape. And they have their own runway here. These are the buildings of DLR, and I had also the pleasure to work for almost 10 years here in this building. And so what else can we say here? Yeah, we have the singular trees and shadow, things we know. Then we talked yesterday already about the effect of the processing in azimuth and range, where we have very, very strong backscatter, radar backscatter. It kind of pauses through here in the two processing directions. Yeah, and of course here having 1 meter resolution, we see also from the pasture or agricultural fields, we see nicely different details in the areas. So this looks like an airborne image, like an optical airborne image. So giving a lot of detail. Then radar is sensitive to water. So if we have the water surface in a flood event, here is one from 2013. That was a very, very large flood in middle Germany. Then usually if you have flooding, at least in Germany, then you also have cloud cover, so it's hard to monitor the extent. Again, another nice advantage for radar. Obviously, same is true if you're monitoring sea ice. Well, whether it's northern or southern hemisphere, sea ice develops, of course, more in the respective hemispherical winter, where you do not have respective illumination to monitor procedures or processes that are necessary to monitor. Here in this case, it's a huge iceberg was cutting off some piece of this glacier in the Antarctica. But you all know monitoring the change of our polar ice caps and the respective sea ice dynamics is important in the context of climate change. So there is no other way than to use radar, actually. Yeah, ocean wave patterns. Just trying something. So ocean wave patterns, we talked about yesterday already, can be nicely seen. So radar is being applied for oceanographic applications. Here, for example, you see the nice Lee effect of that island. So here the surface is smoother. You see different currents coming together. See here the wave patterns. But we also see what we've talked about, the geometric effects here nicely. Layover and foreshortening can be seen, but that was not the focus of the slide. The focus was the wave patterns or the oceanographic features on wind and currents. Well, the oil slicks we talked about yesterday already, so it's nothing new. Subsurface imaging for geology. Here another example, another famous example, comparing Landsat and JERS. So for those of you interested, I don't know, perhaps in arid regions and mapping subsurface geology, of course, L-band, you should apply L-band is the tool. Okay, now let's look into resolution again, just some more considerations, again, from a bit different angle. So what we're seeing here is the angular resolution of an imaging system, and here Michael Eineder brings this nice example to our own eyes. Yeah, so the angular resolution is dependent on the so-called diffraction limit, an angle that is determined by the wavelength and by D, yeah, the aperture. So in our case, our lens. If we, for an example, the human eye from space, if we would fly 1,000 kilometers away, the wavelength, the central wavelength of our eye is 500 nanometers. So divided by the 5 millimeters, which would be the diameter here of our aperture, then the resolution we would be able to see is 100 meters. And if we apply this for a radar sensor, then we would actually, in a real aperture, we would end up with a resolution of 33 kilometers. Here's here some more graphs to follow. So the diffraction limit is obviously hidden here in this term. We have the range, which is the distance to the object. We have the wavelength, yeah, meaning the shorter the wavelength, the better the resolution. And we have this magical D, the aperture, that is being used as a concept in this synthetic aperture radar to extend, to enlarge D to come up to a better geometric resolution. Okay, yeah, in this sense, this is a repetition of what I had explained to you before. So we are extending here the length of our antenna aperture to increase this diffraction possibility and using the Doppler principle. But let's look at some further graphs. He has a nice animation here for the range imaging principle. And I thought it's good to share this with you, also to show perhaps what has been explained yesterday from a different perspective. Yeah, so here we see now the SAR antenna, the antenna beam here to the side. The pulses are being sent out, and every time, depending on the time, of course, the signal goes back to the radar antenna. So it's a complex interaction between sending out and receiving, and obviously then storing the echoes of the transmitted pulses. Also, what this shows nicely, I think, if somebody had problems with understanding that, he shows nicely the wave front. There's one wave front being emitted, and only depending on the time, here the first backscatter signals come back, and then the last are the ones that are in far range. The near range first, and then far range last. So I think from this image, from this image, I can introduce a new term now, the pulse. We have been talking about the pulse repetition frequency, but the pulse is important in the radar processing because it influences the resolution. So this is just a graphic to illustrate, if you ask yourself, how is this done with the transmission and the receiving? The radar antenna cannot receive during transmitting. So it is also, it's always waiting for the received pulses. So here is the transmission. Then in between, you see there is the antenna is being receiving signals. But because of the time lag, it's not immediately the next one. These returns come from an earlier pulse. So this is what these little lines here will show. So just in case, I mean, again, this is a technical background, but it may help a bit more to understand the radar image. Okay, now the following slides go a bit more in depth here to the range resolution. And this is a next technical term, the chirp echo. Now, what is a chirp? The pulses are modulated to be able to increase the energy of the pulses. If a pulse would only stay in or be the carrier frequency would indeed only be one frequency, then it is technically difficult to send out enough energy from a satellite system. And so the chirp again is modulating the used frequency. Still, the center frequency is the one that we have been talking about before, but the chirp has now a certain bandwidth B. And I'm only introducing to you the term because this term, the bandwidth, defines the final range resolution. So the resolution, again, in range is closely connected to these characteristics of the pulse. And I think that is, from my side, this is really in all that you need to know. But it is important if you want to go deeper in radar processing, perhaps you want to acquire, for example, for terasar images, you can actually determine the bandwidth that you want, because with the changing bandwidth, you change the resolution. So this is why it's important that you've heard the concept and why can I choose different bandwidths, for example, when I order a certain radar scene. So that's the whole background. And let me see. Yeah, so here he's comparing how I have been introducing to you the radar wave just as a sine wave, with the amplitude and our wavelength, and a constant frequency. And what is really indeed used technically is this kind of chirp, or it's called a chirp. where the frequency is being modulated. And just at the center, the frequency meets what we call it for the Seabend 5.3 gigahertz, for example. Yeah, that's the center frequency. But with this modulation, we can increase the bandwidth, B, which was important, as we've seen before, to increase the geometric resolution. Okay, and now he's showing how the Sar processing is happening. There is this transmitted signal from the satellite, and then this echo in each single pixel is being compared to this reference chirp, and only if it matches, we get, this is an example for a point scatterer, like a corner reflection from a building, or a calibration equipment like the corner reflector. So this would be a point scatterer. And point scatterers are important also in interferometry because they give a strong signal. We can identify them. For example, if we want to do differential interferometry movements of the surface, then we are focusing on these point scatterers. For Germany, for example, we have a map of point scatterers. Our geological service has published a map of these point scatterers. So, well, everybody applying differential interferometry can focus on a certain point. Again, here, this little example just shows that from a point scatterer with a large returning echo, we get a very nice, strong point signal. Okay. So here comes the resolution again that has been introduced before. But again, these are, I don't want to confuse you with this. I know how much it confused me. But here are some terms or terminologies hidden that you may need. Okay, what happens if the received signal looks very different? Like here, this return, for example. In this case here, two strong reflections, tau is the pulse length. They got mixed up because of the resolution cell hitting two strong backscatterers, then you get respectively two such strong signals. Okay. Good. So this was a few sentences to the range resolution and the importance of the pulse, and that we as a user applying radar images with some sensors, I can, for what we said before, the pulse repetition frequency I can choose, and I can choose the bandwidth to improve the geometric resolution. With the scanning, we saw this image yesterday. There are also different modes. Also, this is technologically something you need to know because you can choose it. Here is one example, the strip map mode, which gives a wider swath, so you get larger images, but obviously with a less geometric resolution. And let's look through the image construction. And again, we are seeing here the echoes as an example again from a point scatterer when it first reaches this antenna beam. So this is now here indicated with the red color. This is the flight line azimuth, and this would be the range. So just going back again. It's in another way of showing what I introduced yesterday. The detection of a signal when it first reaches here the antenna beam width. and following it through time. This is the velocity vector of the satellite. Following it over time, I extend the observation capability and can therefore, applying the Doppler theorem, focus and geometrically focus and increase the resolution in azimuth. So here we go from the real aperture to the full beam width as the synthetic aperture. And there are some interesting connections between the real aperture. Here's the 10 meters that I mentioned before. A small antenna has a very wide beam. So here, for example, this would be 5 kilometers. So the resolution and also the coverage of the ground would be 5 kilometers, from which one wave pattern would be reflected. And if we extend now the observation, or if I would ask how long can I extend the observation, well, I can extend the observation as long as the beam is. So our synthetic antenna actually is as long as the beam width. Now, the synthetic antenna becomes the size of the observational area. So this is why we have now here L, our synthetic antenna is now 5 kilometers, and we can therefore focus to a region, and we observe that region, and now we can focus on 10 meters. So this is, and the range is 850 kilometers, as it would be here. These are ERS1 and 2 parameters, so satellites, but as now for the Sentinel, similar range, similar flight heights. Okay. So let's say very simply geometrically, here it is shown how we extent of the real aperture. So the real length of the antenna system relates to the beam width, and eventually how these 10 meters relate to the focus 10 meters as we have it now at Sentinel-1. And again, this is just another way of showing the first time this object is being observed, then we are closest to the object and we're moving away, or actually it's moving down than the last time we observed it. First time, middle range, or closest acquisition. So and this is the point when that Doppler frequency is exactly the frequency of the emitted energy or the emitted pulse. It's going to be zero Doppler. I think actually this is going into too much technical detail, but for those of you interested in the technical issues, I would really like to refer you very much on the, there are also videos available where Michael Eineder gives this presentation. But here for me, why I'm using them is to introduce you to some of the terms. And it's really up to you how much you then want to go into the processing details or not. But for applications, we just need to know the terms. And I think the reason why I left is, for those interested in this Doppler approach. Now we call this the zero Doppler position, when the antenna is closest to the point, when it, and therefore, like again the analogy with the tone of a passing train, if only if when the train is closest to you, you hear the frequency that the train is emitting. This is the same what's happening here. Then only when you're closest, the point, the backscattering signal is in the emitted frequency. All other positions, where the satellite moves towards the point, here where it moves away, have a changing frequency based on the velocity, of course, of the satellite. And this is what is shown on this next slide. So here we have our reference chirp. And here you see how this is here the satellite would be moving, and this is how the signal changes. But I think this is very, very esoteric to you now. But for engineers, I think this is a lot of joy, how to develop the best possible azimuth resolution, the best possible geometric resolution from such radar signals. Okay. Yeah, but that's what's now interesting us again. How does that image actually look like? And here you see an image that has been processed in range, but where the azimuth processing step is still missing. And here you see what was meant by these singular peaks or these double peaks that we saw before. Here you see how these a strong scatterer, how it stretches into the azimuth direction because of that synthetic aperture radar approach. Because we watch a point target, which would be here in the middle, we watch it over several flight positions, and this observation is then being kind of carried into the image processing. And here's another one. Here's a strong one. So how does the radar image look like? Now, this would be the respective radar image. Then we see here's a strong scatterer. We see also in range that these bright signals are down here. Just go back. It's not exactly the same position. Looks like here's a very strong scatterer. And this is how it would look like. Now, there is one more step that is being done in the so-called Sar processing, is the reduction of the azimuth pixel, because the interesting effect of processing in range and processing in azimuth is two different resolution processing steps, results in rectangular pixels. So the resolution here in range is a different one because it depends only on the time that the signal takes and the incidence angle of the signal. So here in azimuth, we have the chirp, the antenna beam width and the chirp as the resolution elements. And this ends up in rectangular pixels. So again, another step that has to be done to come then to square pixels. And this is, of course, what we want. We want square pixels. So again, this whole excursion for you, because if you work with radar data and you are, one of the formats you can order is the single look complex radar images, which contain the intensity and the phase, and they have rectangular pixels. And so this little excursion, just for you to give you some background, say, why is this rectangular? Yes, it is rectangular because you have two different resolution steps you have to apply. And again, there are the SNAP system that you are learning. There are also these steps are described, and you need to acquire single look complex data when you want to go into interferometry, what we also want to do next. Okay, so then we have these different, this is where the little excursion here started. There are different modes. And Almost all satellites have that. Meanwhile, there is a strip map mode, which gives you a wide swath with a reduced resolution. Here for TerraSAR X, Michael Eineder is very closely involved in TerraSAR X, so he's giving examples of that. Strip map is one of the modes. So then another one is the ScanSAR. So that is a term, a word that is also used for radar sat. It also has a ScanSAR mode. Sentinel has a ScanSAR mode. So here what happens, you see it even goes even a wider swath, 100 kilometers, but with a reduced resolution. So what is happening here is that the antenna beam is swinging back and forth to extend the covered area. And then there's a last one, the spotlight modus, where you focus in a certain area and you see what the satellite is doing here. It's looking forward to focus on an area and then flying by until it is, by looking afterwards, increasing the observation time and thus be able to increase to 1 meter resolution from space. But then you only have a 5 kilometer swath. So these are very generic terms, ScanSAR, strip map, spotlight. And again, this is typical for radar. With the optical data, you don't have such capabilities of illuminating an area specifically, observing it for a longer time. What you collect is reflectances. Except what I just said, there are concepts in hyperspectral remote sensing and in MAP, the next hyperspectral sensor also being launched next year, is one that actually also where the optics focus on a certain area to increase the observation time. In a way, it's a comparable method. Only that here the radiation is not coming from the sun, but from the satellite itself. Okay, so this is, we don't need this. And this I just explained. And now this showing this spotlight modus. Okay, and we come to the last part of the characteristics. Just let me see how many those are. We should, here comes the corner reflectors and some examples. Now, very nice. So we can finish this more technical part of the lectures in the remaining time, but I would still like to have, let's say, let's start it in 3 minutes is not much, 8 minutes. Let's start in 7 minutes, 25 past, 25, please. Just have a short break for the last half an hour. Okay, so see you in 7 minutes. So, welcome back, and let's continue. Some further examples on the characteristics of the Sar images. Okay, so here in the beginning, again, these slides from Michael Einlieder focus on calibration. So there are some examples on the corner reflections, what I had been discussing before. So these are technical terms. Again, those who are not the engineering types, don't be too shocked if there's problems in understanding the concepts, but perhaps there are some of you who are interested in these aspects of radar remote sensing as well. Then please, I can only refer to you, all the EO College material on our website. There are videos and further slides available, but here the idea is in this short time that we have together that you get aware of some of the issues in radar remote sensing. Okay, so the reason why corner reflectors are being used is that, and here is our sigma again, this calibrated radar cross-section can be determined on an exact area. So depending on the size of, here you see the L, depending on the size of that tetraeder, depending on the wavelength you are using, you have a term that you can now implement into the radar equation. So for a sphere, this is also sometimes used. The radius is important. And obviously it is better to have a larger area collecting all the energy of the pulses that hit that corner reflector to have a better signal back on the antenna. And that's what these lobes here meant, that as we saw before, you want to have a strong signal with a very large magnitude, a large main lobe, with a very nicely defined resolution, and not so much these side lobes that only occur in the image if you have such a very strong backscatter as it comes from the corner reflector. That is why corner reflector is being used for calibration. Okay, let's see, yeah, so this was really just again a little excursion, because maybe in some of your work calibration becomes important, and then the issue of perhaps implementing a corner reflector may be of importance. Now we are looking at another aspect that is important for this is the radiometric quality of a radar image. And here we introduce now further terms. I have introduced to you yesterday sigma naught. Yeah, this is not sigma, some say also in German, some say sigma null, but this is really, it's referring to a standardized area, so we call it sigma naught. And this sigma should only refer to a ground range. So usually it refers to the geoid. So here we see the sigma, the sigma naught referring to the ground range of a nominal geoidal surface. So the beta naught is another term. We are looking now at this incidence angle on the surface. Beta naught would be this answer or result or description of our backscatter in slant range when we have no assumption about the terrain. So if no terrain correction can be applied. And so it's here written in bold letters because there are some, this publication went through the radar community where they said it would be better if we only use the term sigma naught if we actually really produce a terrain corrected backscatter calibration. Yeah, so it is better to usually use only the beta zero or beta naught because that is in the radar slant range geometry and does not correct for any local terrain considerations. Okay, and the last one, the gamma naught, would be one for rough surfaces or volumes, where we here look for let me just see where the terrain is included and the incidence angle. So why is this important to discriminate whether we look in the range, slant range, only look at the incidence angle theta, or whether we include alpha, so the local terrain surface? It is important because of this connection of the radar backscatter and the local incidence angle. Yeah, the steeper the angle on a surface, the the larger the backscatter. Remember those graphs of the geometry effects on the backscatter, where we had, when we have foreshortening, we have a very bright return of the slope looking towards the radar antenna. Now this is the extreme case where we would have a steep slope. Yeah, if this alpha angle would be larger and we have a steeper slope, then the incoming radar wavelengths would hit the slope almost vertically. And one effect is the geometry, but the other effect is that the steeper we look, now it's easy to imagine, the steeper we look, the larger is the backscatter term. So into a very specified radiometric calibration, we should always include the local incidence angle. Now, to include the terrain surface, to include here the incidence angle, the local incidence angle of the incoming wave, and not only go by theta, so which is coming from the radar antenna itself, without considering no assumption about the terrain. So, okay, that is why this plea was made. Please call it beta zero or beta naught if you have no terrain correction. And only if you have terrain correction, then you can call it sigma naught or gamma naught. Yeah. And again, this radiometric correction also has its limits because of the geometrical effects. If the terrain is just getting too steep and we're going here towards vertical incidence angles, then of course you cannot correct for that anymore. So what is then one further aspect on this connection between incidence angle, or rather local incidence angle and terrain? It is a very good identifier of the surface roughness, because looking at this little sketch here, you can imagine if this local terrain surface is a smooth surface, an agricultural field perhaps with a relatively smooth surface, or a geological surface that is relatively smooth, then your incoming wave will undergo specular reflection. It will undergo specular reflection away from the sensor. So if that happens, then if it is a smooth surface, then this local incidence angle becomes very important, because the steeper it is, remember the foreshortening effect. The steeper the slope is, if we have a specular reflection, the stronger the signal which is coming back. And then and if the local terrain surface has a large slope, if it is more flat terrain, then we have specular reflection away from the sensor. So the sensitivity to the local terrain, local incidence angle, the sensitivity to the local incidence angle is extreme for smooth surfaces. And if you are interested in mapping agriculture that is on a sloped terrain, or you want to map soil moisture differences, now then you have to take into account this connection to the roughness. So a smooth surface is a problem with respect to the local incidence angle. If this local terrain surface is rough, then we have diffuse scattering in all directions, and this local incidence angle is not as important. Now we still have the geometrical aspects, but if let's say it's not such an extreme slope that would cause a foreshortening, it's a nice slope that you can detect, but then the impact of the local incidence angle is not as large if it is a rough surface. So we have this interplay. That's why I like to say it's rather three things that connect to each other. It's frequency, polarization, and the incidence angle. And to be specific, it would be the local incidence angle, but then you need the terrain model. And on the surface side, it's the roughness, the geometry or structure of your surface, and the water content. So the roughness is closely interacting with that incidence angle under which the surface is being observed. So it's always these three things being connected to each other. Now, if you have a forest on a local terrain surface, forest gives you volume scattering, and volume scattering, again, it doesn't matter from which angle you observe it. Now, then the local incidence angle, again, does not play such a role. The problem is for smooth surfaces. It's not so bad for rough or volume scattering surfaces, but for smooth surfaces. Okay. So, well, this is about radiometry. This is about radiometry. And okay, one more thought on the radiometry. Also, if you're using optical data, you know that topography obviously has a large impact. It's not often corrected. Sometimes you use, or if you use an NDVI, then the ratio kind of calculates the differences out between the illuminated and the shadow side of your topography, but it's also there. So if you want to do a fine work with optical data, you also need a digital elevation model. You need to account for the different solar angle illuminating your surface. Now, so if you go into this detail, like here, because the effect is so dramatic, then this is not really something very different than what you should do with an optical image also. So again, to repeat, this effect of the local incidence angle is especially strong for smooth surfaces. So if your application is agriculture, or maybe geological service, or also snow analysis, I don't know all the application areas you are interested in, then you have to remember that the local incidence angle should be considered in a radiometric correction, for which you need the elevation model. Okay, there's some examples here on the, this is for Rainforest Strip Map. Just to show you the differences, here we would have that beta Naught, the radar brightness. And you see there is no topography included, and you get here for the strip map images, they have quite some different brightnesses. So if you want to compare here radar backscatter values from this scene to this scene, I mean, obviously you have to be very careful because your all over scene brightness is different. Now this would be sigma naught, including local incidence angle. So the elevation model is being considered. And the formula is very simple. Now your sigma naught includes, well, this is beta naught, the calibrated radar cross section, but without topography. In here, the topography comes in. And I mean, obviously, this helps you to eliminate this scene to scene difference, but there's still a little bit. Yeah, and then there is a further one, another approach. This is this gamma naught, what has been mentioned before, and here not the sine of the sinus of the incidence angle is being the tangents for an application-specific calibration. If you know your surface is an isotropic volume scatterer, which is the case for tropical forest, you know this is volume scattering happening, and then you can or should apply another formula. So you see the difference here. There is a difference between sigma naught and gamma naught. Okay. Then there is a slide also explaining the dBs, what we already covered yesterday and at the beginning. Yeah, the backscatter coefficient ratio of the incident power to the reflected power. Yeah, and that is why we get these small numbers below 1. And part of 1, and this is why we end up with the negative dB sigma naught. In dB, this is how you would describe your radar backscatter term. And this is what you find on all kinds of regression graphs, all kinds of analysis time series, and on your axis you write sigma naught in dB. Okay, yeah, backscatter of rainforest. This should be an X-band imager XR. So yeah, this must be from just a little bit confused now because XR should be from the Cersei XR campaign. Probably is processed 1996, but these shuttle emissions were in 94. So now with the X-band, yeah, you do not see so much difference in a tropical forest system, but what you can see still, and this also proves that the X-band has a maximum of a 1 meter penetration into the forest, now because it shows here subtle topographic features. So it kind of stays in this upper part of the canopy, and therefore you can see little river systems, tributaries going here into the larger rivers. But you do not see much differentiation between different vegetation types. Here maybe a little darker, this could be some fields, but that's the problem of this very short wavelength. This is not backscatter of a rainforest, this is backscatter of Mato Grosso, so more an agricultural area. And of course, here you start to see differences, but still subtle with X-band, and there is an optical image next to it, just here showing here this is this meander here, and you see some patterns that, I mean, obviously, depending on the time of the acquisition, this may be nicer visible or not. Here you see the forest area coming up in bright remaining forest, same as along that meander, an old or active river. Also here along the river forest, and you can see this here in the optical image. Again, X-band is with a very short wavelength, only detecting surface differences. So meaning if this is here so black, which means it undergoes specular reflection, this must have possibly been just a plowed field, recently plowed, very small field, a smooth field. And in the river, you see that effect of the currents. So the river is not very dark. Obviously, there is an increased roughness on the surface where the 3 centimeter short X-band wavelength already reacts. So then also some words on the on speckle here from Michael Eineder, and where I want to get it first, here's a little explanation on why sigma naught is dimensionless, because now we are looking at the sum of all these individual scattering elements per area. So the square meter per square meter cancels out. So sigma naught is unit less, but it is indicated as dB because it's in a logarithmic scale. Okay, and here he gives also an example for the speckle effect as discussed before. Now the individual scattering, now if you look at these, okay, and here we see this is the representation of that complex signal containing the amplitude, so the power, the intensity of the signal, and the phase, the phase state of the signal. And now we see these little individual green things. This is what we saw before also, and everything adds up. Yeah, in this case, to a constructive signal, large amplitude, and with a specific phase. The end intensity and the phase. And now he goes on also into speckle statistics, that looking at these individual scattering elements, they are Gaussian distributed, but on the next scale, he shows that it is a difference whether you work with a magnitude, and in this formula represents again intensity and phase, but now the root of the squared sum. Then, because of the character of the signals, it's a Rayleigh distribution, and staying in the intensity, where you just sum up the squared intensity and phase, it is exponential. So again, these are some specifics on the speckle statistics that have an influence on the filtering. And as I know, you do a practical exercise here related to this term, the number of looks, the number of independent sample looks. And this becomes then, here, as you see, the more looks you add, then you change from the Rayleigh distribution to a Gaussian distribution again. But this will be part, I'm pretty sure, of a practical that is given by Misha. Okay, there's also some technical specifics here on the case that is not so relevant for us right now. And here you see the difference of the number of looks. This would be such a single look image where you observe all these different, the impact of speckle on this very high resolution of 1 by 1 meters. And if you average over a number of looks, then the surface here visible, now we are zoomed in this image very much, but you see here a street becomes more consistent black surface. If you zoom out, then the appearance would be much nicer. But what you lose, of course, is also the information on the edge. So that's always the trade-off of using some kind of averaging, which here the multi-looking implements. Okay, in some slides on the penetration of the microwaves, because that's for us as application people, of course, very important. As said earlier, depending on the wavelength, we have different penetration depths in the vegetation. X-band, the experience says it's about 1 meter, depending, of course, on the density of the forest. Seabed is really a problem because very much depending on the characteristics of the vegetation volume, on the density, on the amount of water, on the size of the leaves. Now, the penetration depth can be everything between 3 meters, 5 meters, 10 meters. So it's very hard to say where the scattering is actually happening. With L-band, you can be very sure, very certain you will always get a backscatter from an interaction of the ground and the trunk, and you will penetrate through the vegetation canopy. So as a matter of fact, also the soil moisture below a forest can have an impact here on the backscatter. So with next year, with the launch of NISAR, this will be a nice opportunity to look into time series, because, for example, for detecting moisture under forest, of course, you need a good time series to get out of the changes of the vegetation itself. Okay, with dry soil, same thing, different penetration depths up to several meters. And for glacier ice or snow, same thing. X-band will stay on top. C-band will have penetration further into different snow or ice layers, and L-band very much so. Perhaps you would even get a backscatter from the below surface. Here important is that because of the crystalline structure of frozen water, your penetration depth here is indeed very deep. And a nice example here about the radar ground penetration from some publications. They did measurements below the sand layer in this desert to observe where the signal actually comes from and illustrate a bit what we see here on that image. So we have a strong return where we have only a sand layer on top, and we get weaker returns here from the old riverbeds because of the longer penetration path to the deposits below. And the signal obviously has to pass through these alluvial sediments. And I think on the next slide, there's even some numbers. Now, where it is listed that you have here penetration depth up to 2 meters in dry sand. And they actually buried receivers under the sand. So it's just showing how water governs the radar backscatter. If there is no water, or the water is frozen, as in snow, you have quite a distinctive penetration depth. So, and some further examples. Yeah, let me see, is there anything on the list we didn't have before? Yeah, or the Spanish X-band I didn't mention. This is a replica of Terrassa X Tandem X. Cosmos Skymet, very important Italian development in X-band, and he is not listing here the commercial ones, but again, in the commercial frame, there's a lot of development. Yeah, RADARSAT constellation missions. Okay, And again, I would like, and I'm sorry, I would think that all of you have touched Sentinel-1 data before, but if not, then you do it now in the practicals. The launch 2014, the first one, and then the second one in 2016. And again, there are in the history of the European Seabend development, ES1-2, the first ones at Envisat, data is freely available. 12-day repeat, but 6-day, if you include the Sentinel-1B, obviously that makes sense. And there must also, in Russia, there should be much, the temporal resolution should be much better, like in Thuringia, because of the overlapping swaths. So you could, then you have different incidence angles, obviously, but you can look at the different overlap. Standard mode is the image wide swath. It's 250 kilometers, and you see a 5 by 20 meter resolution. This is now here an example for this, the rectangular pixels, but of course they are then being corrected to quadratic pixels, but this comes from the different range and azimuth resolution background. Then there is a strip map mode that's 80 kilometer width and has 5 by 9 meter resolution. This is what we usually use. Then the square pixels are 10 by 10 meters. That's for us the standard, because in Thuringia is not very large. The 120 kilometers extension, 100 kilometers in width. So we do not need a wide swath coverage. But this may be for Russia, covering Russian territory, more applicable. Okay, well, different applications, and obviously this Copernicus program that I have mentioned before, it's paid by the European taxpayer through the European Commission. And it has been developed for all these kind of applications, and especially obviously for emergency management, floods, forest fires, and for security applications, but all in this 10 meter resolution space. Yeah, something done here with Sentinel-1A was, and it went through the media, was the increased dynamic glacier outlets on the Greenland coast. So you can find a lot also updated material here on the internet. And of course, having a system like Sentinel in space that continuously monitors the ice condition is the best, let's say, the best observation tool to follow on what we are producing with climate change, what the results